This is lecture number 38 of the course ME314 Fluid Mechanics 2, and this is the second lecture of this week. In the last lecture, we have seen the calculating the drag coefficients if we have a knowledge, calculating the drag force if we have a knowledge of drag coefficients. So we will extend the same thing. We will see different geometries having the different drag coefficients. So we will look into drag coefficient for different common geometries. We will look into the concept of the drafting, and there is a term called fairing, and there would be the drag reduction or drag come into play in the nature as we see different birds and insects fly. And then we will go into the applications for which the drag reduction is possible, and we will look into how the drag coefficient is actually, or the drag force rather, is actually measured through experiments. So we look into this table here. What we see is low Reynolds number drag coefficient, so which essentially says that this value of the drag coefficient, which is actually the value of the drag coefficient is 20.4 over Reynolds number for this particular geometry, is valid only for low Reynolds number. And here the Reynolds number is defined particularly because this would be the free stream velocity, and A is the the area which is actually the frontal area, and in that case this would be the for example, where characteristic length is diameter. So for all these geometries, area to be calculated by pi by 4 d square. So it is very important whenever you are working out with different tables for finding out drag coefficients. So you must look for the applicability. For example, here this relation is applicable for low Reynolds number when Reynolds number is less than 1. So it means you need to use different tables for different values of Reynolds number. We already have seen that the drag coefficient is for a given shape, it is a function of Reynolds number. If shape is changing, then it would be a function of shape and Reynolds number. So if you look at here, the drag coefficient is as the Reynolds number is increasing, the drag coefficient is decreasing. So it is an inverse relationship, and we have seen that that is true for laminar flows, in which the friction coefficient is also a decreasing function as the Reynolds number is increasing. So the same is true in this case as well, and we can see this value further drops in the drag coefficient if instead of a vertical plate you have a horizontal plate. So because we know that in this case the friction and the pressure component both are taking part, and in the flat plate only the pressure component is not that significant compared with the friction component of the drag. If you see that sphere whose diameter is d, then it is actually the same drag coefficient. So it is very interesting because here the frontal area is the diameter, and we have calculated this frontal area based on this cross-sectional area, and so here also if you cut that, you will form a circle, and so the frontal area would be that cross-sectional area. So it doesn't know the shape, it just know this frontal area. And in case of hemisphere, this drag coefficient has decreases. So what we do is, if you look them closely, if drag coefficient is 24 over Reynolds number, and Reynolds and drag coefficient multiplied together, it would be a 20.4 is a number. So 20.4, this number is actually a constant. So for different geometries, you see for low value of Reynolds number, this product of drag coefficient in Reynolds number is a constant value. So this is an interesting result. So you will see for a given geometry and given Reynolds number, the product of the drag coefficient and Reynolds number would be some constant value. For example, here the constant value is 20.4, here it is 13.6, and here is 24.0, and here is 22.2. So one notion that is important is whenever you're looking at different handbooks and tables working out drag coefficient, you must look at the how they are defined, Reynolds number, and how the reference area is defined, and how at what values of Reynolds number the drag coefficient is applicable. So you cannot use them blindly. Okay, now look at another table for calculating the drag coefficient. So what we look here is these are two-dimensional bodies where Reynolds number is something greater than 10 to the power 4. So it is for somewhat higher Reynolds number, and the definition of the frontal area is actually B is actually the length of those sections, and D is actually this frontal length. So area would be B times D. So here this frontal area and the drag coefficient times the area times half rho V square, there's dynamic pressure, and where V is the upstream velocity. So the definition for frontal area and the definitions for the applicability of Reynolds number is different in this table. So that's why I've put this information in the table too. So if you look at this, if you have a square rod, so of length B, and its vertical height is capital D, then for that range of Reynolds number, the average drag coefficient you observe is 2.2, and just make that D is the same, but instead of sharp corners, if you have a round corners, and the ratio of the radius, this what you call it, a fillet radius is over diameter is, if it is 0.2, then your drag coefficient has been reduced from 2.2 to 1.2. So it means the power which is used in overcoming the drag has reduced from 2.2 to 1.2. If you take its percentage, it could be a huge reduction in the drag coefficient. So just by making the, instead of sharp corners, if you have round corners, so we can reduce the drag quite a lot. For circular cylinder, the drag coefficient is different if it is a laminar flow, as well as it is a turbulent flow. So obviously you need to have some critical Reynolds number in that case, and for turbulent, if it is much higher than the critical Reynolds number, then you have some lower drag coefficient. If this rod is a rectangular rod having the sharp corners, and then the drag coefficient would be a ratio of L over D. So when L over D is 0, it means it's just a vertical plate, then your drag coefficient is 1.9. So if you're increasing that length L here, and the drag coefficient is increasing, and then after reaching L over D 1, it is this value, and then it's getting dropped in the drag coefficient. So depending upon the shape and size of the geometry, the drag coefficient is varying. And if you have round corners, then you have at L over D ratio, your drag coefficient would be 1.2. If you have this elliptical cross section, and this at different values of L over D, as well as when your condition of Reynolds number changes. So Reynolds number is defined based on this characteristic length d and the free stream velocity. So for turbulent flow you have a different drag coefficient, and for laminar you have a different drag coefficient. In this table also you see the same thing, that the reference area is defined, particularly the Reynolds number is defined, the range of Reynolds number is defined, and the definition of the drag coefficient, which is the drag force over this dynamic pressure times area, and different values of R over D, this rounded corners, your drag coefficient is varying. So if R over D is increasing, increasing, so more rounded here you have, then lesser would be your drag coefficient. For this equilateral triangle, and we look at these two-dimensional objects, it means their length is actually the B here, which is not shown, which is in this depth actually. So this B is much greater than this other dimensions, like capital D here, which is your characteristic length. So because in this definition of Reynolds number, rho, u, and characteristic length. So for all these geometries, this dimension D is actually a characteristic length. So need to be careful about how to calculate Reynolds number, because the drag coefficient would be a function of Reynolds number. And interestingly, if you see this arrows here, so for example, if the flow is taking place like this, so it means the streamlines are passing like that, so it means your drag coefficient is much smaller. But if flow is in the opposite direction, so this arrow is representing that if the flow is in its opposite direction, then you are facing this vertical length, and then the drag coefficients are much higher. So depending upon this arrow is representing, actually this arrow is representing this one direction, because it is same actually, but in this shape, a triangular shape, this arrow is representing the direction. If this is the direction, then you have a different drag coefficient. So be careful about looking at different tables now. For example, in this semicircular shell, or if it is a semicircular cylinder. So if it is a semicircular shell, it means it is just like a shell or a cup shape, and if direction is from this way, then it is experiencing quite a high drag, because this like as a surface of this parachute from inside. And if it is an outside surface, then streamlines would go like this, so you have some lower value of the drag coefficient. Similarly, for both directions, you have a higher drag if flow is from this direction. If the flow is from this direction, then streamline, then you expect some lower drag coefficient. So we need to be careful about the direction of the velocity, the Reynolds number, and the characteristic length, so that we can calculate the right value of the drag coefficient. For this geometry, like triangular cross sections or some eye section of the beam, for triangular cross sections, obviously once you are from this side, some higher drag, once you are from this side, you have some lower drag. And here this D is used to calculate the Reynolds number, and in all that direction this D is the characteristic length actually, and they are all in the order of 10 to the power 4, greater than 10 to the power 4. This is the range of Reynolds number to which this would be the average value of the drag coefficient. And if you look this, earlier we have these all two-dimensional geometries. Now we look at this three-dimensional geometry. So you have a solid hemisphere. So the sphere is cut into two parts, and from this side you experience a higher drag, and from this side we experience a lower drag of 0.42. And here the reference area is defined by a different expression, which is the pi by 4 d square is the definition for this 3D geometries. And this is actually a thin disk, so the thickness of the disk is not that important. So in that case the drag coefficient is greater than 1, that is 1.1 for Reynolds number 10 to the power 3, and the definition of Reynolds number is rho u d over mu, and u is actually the free stream velocity. And if you have a circular rod where your direction of flow is parallel to the flow, so in that case the ratio of L over D is determining the drag coefficient. And we see other geometries, like let's say the cone shape. So if flow is from in this direction, so this is the value of the drag coefficient. If theta is increasing this cone angle, then your drag coefficient is changing. So even for cube, if you see that if it is placed with the characteristic length of diameter d, then your reference area would be not pi by 4 d square, but it is some different d square. So we must look at the definition of that reference area in order to know exactly the right value of the drag coefficient. So here if you see the same direction of flow, but just I have changed the orientation of the this square section. So once you make it this shape, like a diamond like shape, then it's there is a significant drop in from 1.05 to 0.8, the drop in the drag coefficient. And if you have streamlined bodies like this, just like we call it a teardrop shape. So teardrop shape is when water in a tear is actually drops in air, and it is facing very small amount of resistance in air, then it is actually called as a teardrop shape. And most of the time in vehicles also we talk about designing the vehicle in such a manner that your body is streamlined. Actually it is like a so-called teardrop shape. So you could have some very low value of the drag coefficient. So for example, for this particular shape, the drag coefficient is pretty low, which is for this high value of Reynolds number. If we look at parachutes that is being dropped in air and facing air resistance, and this 1.4 is the value of the drag coefficient. So if you have parabolic dish and then this diameter, this from the edges, if it is, and we can see that if direction of flow is in this manner, you have some higher drag, and if from direction of air is from this side, then it is some lower value of the drag. And for an average human being, once it is in the standing position, so your drag coefficient is not given here. Actually the product of drag coefficient and the frontal area is given. So in that standing position, the product of frontal area and the drag coefficient. So keep in mind, so you have to divide by the frontal area in order to know this drag coefficient. And in sitting position it is different because you have some lesser drag and lesser area, frontal area. So if you are just crouching position, you further decrease the product of drag coefficient and the frontal area. So actually you are not just even reducing the drag by changing the shape, as well as changing the frontal area as well, because both are required in calculating this drag force. And for flag, this area is the product of this would be a reference area, and as the length over d is changing, the drag coefficient is changing. So there is no one single value of the drag coefficient. Different buildings, tall structures have usually the drag coefficient in order of 1.4, and you have six carriage passenger train based on their frontal area, because the shape is also important, and your drag coefficient is 1.8. And if you look at bikes, if the rider is in the upright position, and the frontal area is 5.5, then the drag coefficient is 1.1. If it is just bent downwards in the racing position, then with this the frontal area has reduced as well as the drag coefficient has been reduced. And this is what actually called as drafting. So this is there is a pressure distribution due to this, the person in the front and the person in the racer in the that following that cyclist would be experiencing less drag. So that is actually called as drafting. And if the cyclist have some streamlined body, and then there is a huge reduction in the drag coefficient. So what actually the term drafting is, actually when you draft the drag coefficient of bodies following other moving bodies closely can be reduced, and this effect is called as drafting. So, and that happens is because in the first cyclist would be facing some higher pressure on the front and some lower pressure at the rear side. So, and this lower pressure region will be exposed to the front of the cyclist which is following. Then this there would be a lesser drag on the person who is following the first cyclist. So once you are moving in such a manner that you are actually following the object which is in your front, so all the drag has been reduced by the cyclist in the front, so the lesser drag would be experienced by the cyclist who is following the cyclist. So this effect is called as drafting, and the technical name for such a thing in cyclist, even on the vehicles in the highway also, you can reduce your drag by just do this drafting. So just following the car in front of you, so you will be in the region of lower pressure region. So it means for your frontal pressure would be the lower pressure, and so your rear pressure would be further lower. So the pressure distribution changes, and that reduces the pressure drag component. Different geometries, like for example in the tractors, so there is a prime mover and there is a carriage. So this prime mover is actually carrying the carriage, and we will go into this fairing, what is mean by the fairing, but just look at the trees at different wind speeds. They have different value of the drag coefficient, because we know the drag coefficient is a function of Reynolds number. So if speed is changing, the Reynolds number is changing, and once the Reynolds number is changing, the drag coefficient is changing. And in case of objects like fully immersed in water like fish, and for that dolphin at that Reynolds number, assuming the length of the dolphin is considered as a flat plate, then it's due to that friction component, the drag coefficient would be 0.0031. And so it is here the reference area is not the frontal area but the wetted area. So we know the concept of the wetted area from your internal flow, that the wetted area your hydraulic diameter is your wetted area over perimeter. So 4 times of the wetted area over the perimeter is the definition for hydraulic diameter. So here this area is actually not the frontal area but the wetted area. So, and the objects like birds which are flying in air, then they actually reduces the drag by reduces their frontal area. And we will see in the later part as well how this in nature the drag coefficient, they are actually helping themselves in reducing the drag so that less energy to be used in flying. What this fairing is actually, fairing is nothing, just using some external part or an external structure made up of metal or plastic to be added in order to make the object streamlined. So on the roof this part is added and this deflector is added, so which make the streamline object shape becomes more streamlined. This is actually called as fairing. And you see there is always a gap between the prime mover and the trailer, and so if you seal that gap so that the air there is no pressure loss here, so some higher pressure in the upstream and some lower pressure in that gap, so this causes pressure drag. So get rid of this pressure drag is actually this gap is creating a difference of pressure and the pressure drag. So if you just seal this gap, you will be able to reduce the drag coefficient. So without sealing it was 0.76 and you just reduce from 0.76 to 0.7 with the same frontal area. Without fairing, you see the drag coefficient was 0.97. So the fairing, by adding the deflector, this extra part which actually helps in streamlining the body, so that is actually called as fairing. This fairing has reduced the drag coefficient from 0.96 to 0.76, and this fairing is used in at so many vehicles, like for example in motorcycles. So you see this plastic shape body is used in the front in order to make the streamlined more the shape of the body is more streamlined, especially these high speed heavy bikes. It is very common. And even such shapes like in car racing also, you see, say this plastic part is added, which is actually making the streamlined body more streamlined. And in this cycling also, the wheel is a rough surface and is offering friction drag. So there is a smooth shape, streamlined body, a plastic structure is added, which actually reduces the drag or make the shape more streamlined. And even in this aircraft, the wheels are offering drag, and these wheels are covered with this plastic shape, aerodynamic shape, which reduces the drags. Once it reduces the drag, it reduces the energy consumption. In nature also, the drag reduction takes place. For example, the birds like eagles, what they do is they extend their beak forward, so that reduces their frontal area, and their feet is also they fold backward during the flight, so that the shape becomes more streamlined. So this is how the birds reduces their drag, and the energy which is they save some energy which is required in the flying. And sometimes you see this V formation takes place. So this is actually just like fairing effect. So no, not fairing, it is a drafting effect. So the front one is actually facing more drag than the those who are following the front one is actually having less drag. So and one more thing they do is, because we already have seen the drag is changed with the oscillation and the rotation, so they make the wings motion align with each other in such a manner that there is because the drag as well as the lift both are there. So what they do is they gain the lift by from the rising air, they call it upwash, and uh, uh, reduce the drag with sinking air, that is called as downwash. And so there are a lot of other benefits. This drafting is one of them, and in the birds in the long distance flying, what they do is they change their formation. So once this one is become tired, so it goes to the back in the queue, and this next one come to the place. So in this way they change their energy, and the energy is distributed among all birds. So and this V formation quite helps them quite a lot, and not just the drag reduction, but one more effect, that is actually the heat transfer, because they loses energy, heat of their body, and once they are consuming more energy, so their body temperature also being affected. So once they are doing this P formation and use that drafting, then their body doesn't lose heat that quickly. So that also affects the fluid flow as well as the heat transfers, and that is present in this natural. And so many flies and so many birds these different formations in order to become reducing the drag. And even the marine fish also do the same thing, they reduce the drag just like ships. So they are changing their maneuvers, and so they make their body more streamlined, and so that it has less drag. This drag reduction is actually contributing quite a lot in case of pumping power, because in not in external flow but even in internal flow, when fluid is flowing in a inner bounded walls, then what they do is the friction occurs at the fluid and solid interface. So what they do is, in oil pipelines they introduce a low viscosity fluid in the annular core of the water. So actually water is not in direct contact with the solid surface of the pipe, but the low viscosity fluid is in direct contact with the pipe, and this friction is very much close to the wall. So in this annular core the friction is being reduced even up to 60%. So once the friction is reduced, so the pumping power requirement for long distance pipeline is this is quite a good saving. Sometimes this in the liquid flows they dissolve some additives, like high molecular weight polymer is added, it's injected in the pipeline. So this is small amount of polymer actually reduces the friction by changing the viscosity quite a lot. So lot of friction is being reduced by adding those additives even in small quantity, and your power consumption is being reduced even up to 60%. In aircrafts and in the different objects, even in ships and different yachts, people use different so-called stream-oriented surface grooves. They are called sometimes V grooves, or they are called microblades or riblets. So these are of very small size. For example, if this length is 10 meters, then it is 0.5 millimeter. This riblets are being added. So that's really help in reducing the turbulent drag actually. So because we see this turbulent boundary layer is being disturbed by that grooves and these riblets, which reduces the friction even up to 8%. I mean, in turbulent flows, we know there's some eddies formation takes place in some large eddies and some smaller eddies. So what they do is they make the structure in such a manner so that the large eddies breaks up into smaller eddies. So this reduces turbulent friction up to 10%. So some small structures to be added to the surfaces. In air, microbubbles are injected to the walls of the water flow to create a very low shear bubble blanket. So, as we know, the air is less viscous than water. So, these microbubbles are injected in the water flow. So that this air has low viscosity, so have a low shear stress and consequently low drag, and significant reduction of the drag can be observed. And we already have seen this oscillation and the rotation could be have an impact on the drag coefficient. So sometimes this in the transverse direction, so in the vertical direction, if it is a horizontal direction of the flow, then in the normal to that horizontal, that would be the transverse direction. So if this wall is oscillating, that actually reduces the turbulent friction by 30%. So there are different techniques used for reducing in different applications, not just restricted to external flows. I mean, how to measure the drag is in the wind tunnel. The objects cannot be moved, but the air can be moved, and the force is measured through some different sort of force transducers. So we'll be able to measure the drag force. We know the frontal area, and we know the drag force, we know the wind speed. We can work out those drag coefficients, and obviously these drag coefficients are the average drag coefficients. So this is how we can measure drag coefficients in an experiment. So this is where I stop today's lecture here.